Hi everybody, this is Siavash from PinkInfinity.net. Welcome to my first ever math class. I suddenly feel like I want to talk about homotopy extension property. Maybe recently a lot of my friends asked me to give them some intuition about a proposition in Hatcher book. And I think by myself, maybe it's not bad to record a video about it. Maybe I can help you to get a better intuition about the theorem too. So, in this section, I'm looking forward to prove a theorem or proposition, if I want to be precise, for you in take three video. Okay, it's the first section. I want to go very slowly to help you to make a better connection with the proposition. Okay, without wasting any time, let's get started. Okay, this is the proposition I want to talk in this section. I want to prove this proposition for you. Absolutely, you should study the previous section before watching this video. I want to talk about homotopy extension property. There is a definition here, and I want to prove this proposition for you. Okay, because the equality of the deformation retraction with homotopy extension property, we want to prove there is a deformation retraction between this and this space. Okay, let's start. Okay, in this section, I want to prove the proposition for very special cases. Okay, I assume X is Dn and A is Dn in 0 union with boundary of Dn in I. Okay, I want to prove theorem in this limited case because the main proof is come from here somehow. It is the core of our proof. Okay, it's not very hard proof, but if you understand this case very well, the main proof is not very hard to understand. Even I want to limit it more, okay, and put 1 to n, sorry. So in this section, I'm trying to prove the proposition just for this case, okay? And A equal to D1 in 0 equal union, with D1 in I. Okay, we want to talk about this case and this case, and you will see there is no difference between them because I won't give you an intuition about it. So it's better to we talk about it, for example, in two-dimensional cases, one-dimensional cases, because it's very hard to understand, for example, 10-dimensional object. Okay, so if we start from one-dimensional topological object, it may help us to make a better connection to the main theorem. Okay, so forget about this case first. So let's start to prove this. Okay, to prove this, first we need a retraction function. Okay, we should find the function retract x to this space. Okay, it's gonna be our first step. Okay, don't forget in this case x is d1 and a is boundary of d1. Okay, maybe I should. Okay, it's better. Okay, so let's start. First, it's d1. Let me draw it thicker. Okay. Let me draw it with different color because I want to do something. Okay, it's absolutely feel. Okay, so this area is d1. Okay, let me write it for you. This is d1 and the whole object is d1 in I. Okay, to give you better image of that. Okay, this is d1 and this is I. We are going to find a retraction to deform this space to this one. Okay, let me make a copy of it. Okay, so okay, it's very good. So we want something like this. Okay, we want a map. Do this for us. Okay, this is d1 plus, in d1 in 0 union 1 with boundary. Okay, inside is disappear and we just have the boundaries. Okay, okay, so how we should do this? Okay, there is a very fantastic method to do this, is that we define a radial projection from a point, from an upper point of or a space to this. Okay, for example, something like this, okay, like this. Okay, let me put some arrows to give a better image of what's happening here. Okay, as you see, if we define a projection from here to our space, we can easily get this retraction. Okay, this point is mapped to this point mapped to this point, this point mapped to this point, and all of the point is mapping to a target point. For example, this point mapped to this point mapped to this point, and we get our retraction. Okay, so in this, with this radial projection, we are gonna have a retraction. So the first part is solved. Okay, because we don't use the dimension of d1, okay, we can consider it, we solve it for example dn. Okay, because it's not related to, for example, any dimension. Okay, you can choose a point to project your point. For example, if this is our axis, Okay, we embed our D1 into R2. Okay, you can consider this point, for example, 0 and 5. Okay, if we are in n-dimensional space, you can imagine we have something like this: 0, 0, 0 to, for example, 5. Okay, there's no difference. So we actually have a retraction for arbitrary dn. Okay, so and that's the cause I just want to talk about d1, because there is no difference between d1 and dn in our case. Okay, let me write it more clear. Okay, let me show you what happened in D2 case. Okay, because my goal is give you good intuition about the subject. So I design a 3D model for you to see what happened in three-dimensional cases. Okay, if you see, if we have, sorry, okay, let me move it. Okay, if you see, we have a T2, sorry, not T2, D2 in I, and we are, what happened for my objects? What happened for them? Why they are disappearing? Okay, we have a retraction from this space, from this space to this space, and it is our projection. If you see, we define a projection here. Okay, with this projection, okay, with this projection, we have a retraction from this space to this space. Okay, we go from, for example, a normal cylinder to a somehow empty cup. Okay, this is a two-dimensional cases because we have no, for example, software right now can draw n-dimensional objects. This is the best thing I can do to give you the intuition what exactly happens. So we have a projection with this radial projection. We have a retraction function between this space and this space, and as I already told you, this is not related to the dimension. Okay, you can consider in 2 is n. For example, we already, with this intuition, we already proving, for example, 10 dimension, 11 dimension, 20 dimension. For any arbitrarian or a state is still true. Okay, so let's continue and finish or prove for this special case. Okay, let me continue. So okay, but to complete or prove, it's not enough to just have a one retraction from this space to this space. We need a family of map to do this. We want to do this along the time interval. Okay, we need a homotopy to do it for us. So how we can have a homotopy in this case? Okay, let me copy this object to another clean plan. What happened? Please don't hang. Okay, what happened to them? Okay, try. There are. Okay, it's not very good. So let's draw it from scratch. Okay, it's not very important. Okay, so let me draw it quickly. So we need a family of the projection, family of this map. Okay, and first let me introduce the map for why this happened. Okay. Okay, let me. Okay. Okay. I think I solved the problem. Okay. So we have this retraction here, and we want to build a family of them, define a homotopy between this space to this one with help of or retraction. Okay, so to do this, okay, it's very easy. It's a very important part. Okay, I want to define our family like this, and I show you what happening when we define it. Okay, define RT in this way. Okay, T times R plus one minus T in identity. It's not a very beautiful identity. Okay, I never like my handwriting. Okay, with this function we have a family, we have a homotopy between these two spaces. Okay, this is a valid, okay, because we are living in a convex space. It's very important. For example, when I try to come from this point to this point, okay, because this line is, because all of this line is placed inside, it's very important, is placed inside or cylinder, okay, we can actually do it smoothly. For example, go this far in the first step, go this far in the next step, and eventually reach the point. It because we live in a convex space. Okay, for example, you can take this path to reach this point. Okay, we should stay in our spaces. We just use Rn, okay, to produce our projection, to produce our retraction. Okay, this is valid because all of point move in, all of point in their journey is placed inside the cylinder. They never leave the cylinder. For example, when we trying to map this point to this point, we never leave the cylinder like this. Okay, you should always be inside the cylinder. And because our cylinder is a convex space, we can define something like this. Okay, and with this we actually prove our statement for the end. Okay, but I won't give you some intuition what happening in this interval of time. Okay, So let me finish this section to show you how this function works. Okay? So let me give some copy. Okay, what happened? Okay, let me give some copy of this. Okay, put here another copy, put it here. Okay, it's good. Okay, for example, imagine we have R, for example, 0.1. Okay, with this projection. Okay, with this projection, we shouldn't go all the way. For example, maybe it's enough for this case. It's just example. Okay, I just want to give you an intuition. Okay, we just need to do this. For example, come this far, this far, this far, this far, and this far. So for example, in the another step, we get something like this. So for example, in this time, our space is deformed to this space. Okay, and for example, in this time, our point, our 0 point, for example, 7 reach in this space. Okay, and eventually, let me, okay, in the final stage, reach this. Okay, so there is a lot of map occurred here. So we deform our space through the time to reach this space. Okay, this is the core concept of deformation retract. Okay, so we make a deformation retraction from our retraction. Okay, we go from here to this space, from here to here, along through the time interval start in the 0 and finish in the 1. Okay, and that's it. So we prove our theorem or proposition for these cases. Okay, because we didn't use any properties of the or dimension. Okay, actually we prove it for x, dn, and a boundary of dn. So we prove it for any arbitrary dimension. Okay, so if we have a pair CW pair of a disk and its boundary, we prove it has a homotopy extension property. In the next session, we go forward and prove it for another CW pair, and maybe in our third video we prove it for general cases. I hope you enjoy it and I can give you good intuition about it. And if you like my video, don't forget to like it and subscribe my channel, and thank you for watching. See you later.